Okay, thank you. But actually, I didn't expect to be the final speaker. I came to know that after 5 years. I don't know why. But anyway, of course, it's a great pleasure to be here again, especially this time to celebrate my old friend Spencer's 65th birthday. And actually, I met Spencer 1976, so more than 40 years ago, in New York. Actually, I'm elder than Spencer by 4 years. And at that time, I already have a permanent position in Japan, but Spencer's great mentor, Sakita, kindly offered me an opportunity of coming to United States as a postdoctoral research associate at the City University of New York. So, so I arrived sometime September or maybe end of August in 1976, and I came to my new office. Then, almost simultaneously, some young, very energetic-looking young man appeared and said, "I want to discuss with you." so I'm a little upset because I have no time to settle down in my new office. But I listened to him explaining what he wanted to discuss, and somehow the discussion began. Okay. So after that, we are discussing almost every day, and sometimes discussion becomes very heated. And actually, we both lived in international house, as you. So like we had that, you are also there, although we have no overlap. And sometimes we discussed even in my rooms. He used to come to my room and made discussions and conversation on everything. And after conversation or discussions, we are used to listen to music. I have some reasonable audio system and a collection of classical record of classical music, so we listen together. So in that way, we have very intense connection and discussions, and there is one outcome. Oh, maybe before going to that, I'll explain this. Oh, sorry. Which one is? Okay. Yeah, this is yeah. Oh, maybe I'm not used to this. Okay. Here.
Yeah, just one. Yeah. This is forward. This is back.
Yes. Okay. This is one. Yeah. Okay. So this is a photograph we've taken together. When we attend together, there's a Bengaluru Institute, 1977. So that is 1 year after our acquaintance. And because of this intense connection, we have one outcome, and that is the paper. We have only one joint paper. So this is the one Avinash mentioned in his talk. And so I haven't, it's not necessary to explain anything about that. Avinash already briefly explained the content of this work. The reason why I put this paper here is that as I have some outline here. Oh, again, sorry. So here, general gauges and so independent dynamical role of surface variables defined at spatial infinity. There are two factors here, and in some remote sense, actually today's talk it has some parallel with these two facts. Of course, in an entirely different context, but maybe you may recognize that. So okay, I come to my main content. So today's title is Covariantized Matrix Theory. And actually, I put the paper about this last March. And I also put on archive a lecture note, which is actually delivered around the same time last year in some small workshop in Japan. So if you're interested in my talk today, please look at that. Okay. So actually, I go back to the past, 20 years. Okay. Matrix theory was born around 20 years ago. So I just go back to that time, and if I'm fortunate, then I wish to make it present and hopefully future. Okay? And so I'll first explain what is the motivation to covariantized matrix theory. As you know, oh, again, I made a mistake. Sorry. Okay. So to make matrix theory covariant, obviously we need some kind of higher symmetry. Okay. And for that, actually, I borrow some old idea due to Nambu. And this is also appropriate to this occasion because Nambu was also his great mentor. And also, I admire Nambu. So based on this old idea of Nambu, I generalize that structure in some way and derive some kind of higher gauge symmetry. And on the basis of that, I propose a covariantized version of matrix theory. So that's what I'm going to do. So maybe everyone knows that what is BFFS conjecture, so I don't explain that. This effective low energy theory of the deserblings interpreted as a kind of approximate description in some particular infinite momentum frame for by interpreting these zeros as a kind of patterns for all dynamical objects of M theory. And sometime after this proposal, actually still further very bold conjecture was made, first by Ashkint and also supported by Seiberg and Sen and plus many others, that this theory may be a kind of exact theory in a particular light front frame with a compactified right-right direction. And in this case, so I'm very sorry. I'm used to do this. Okay. So this non-relativistic looking Hamiltonian is actually being interpreted as an exact relativistic Maxwell condition in this way. Okay. That was essentially what Susskind proposed. And if one of the very remarkable characteristics of this right-right compactification is that in spite of compactification, these momentum along this compactified direction and also compactification radius can be interpreted as a continuous variables because that can be changed continuously by making boost transformations along these right-right directions. So suppose that this very bold hypothesis is correct, then of course there is presumptions for this hypothesis. That is, this Hamiltonian should be physically equivalent with the Lorentz invariant mass square. Mass square means this from mass in the center mass plane, even for finite and fixed n. Then this must be true in arbitrary Lorentz way, and hence there should exist a Lorentz covariant formulation of matrix theory such that we obtain this Hamiltonian with appropriate gauge after we make appropriate gauge fixing condition is okay. So this obviously needs some kind of higher symmetry because we have to treat all 11 dimensions on an equal footing, introducing 11-dimensional matrix, not only in this transverse directions. But of course, maybe this is I think this is a very natural idea, but unfortunately, this remained unsolved for 20 years. So what I'm going to do today is just propose resolution against this proposal. Okay. So is there any clue to do that? that, as I said, I borrowed some old idea by Nambu. Some of you may know that, or may heard of this Nambu bracket. And this Nambu bracket naturally appears in classical theory membranes. If you write down this classical Lagrangian like this, and this quantity is, this is of course nothing but just the Jacobian to define volume element, but actually this is Nambu proposed some kind of evolution in terms of using this Jacobian. And so let us call this transformation, let us define this transformation like this. And this, of course, is a particular form of three-dimensional volume-preserving deformations. And as you know, if you make some gauge fixing, like cone gauge, this reduces to this two-dimensional area-preserving deformation. And this is, of course, is reinterpreted or generalized or extended to this matrix transformation in this usual form. So the question is, what does correspond to this generalized transformation in terms of matrices? That is the question. And actually, I initiated this problem almost 20 years ago with some young collaborators here. But we are not successful in doing that. But in any way, as a byproduct, we propose two possible discretization of Nambu bracket. First one is using square matrices joined with some auxiliary variables. And another possibility, we also started with using some kind of cubic matrices or tensors, Sri-Lankan tensors. But today, in the present work, we developed the approach 1, because simplest to do is just using matrices and extend the number of matrices to 11 from 9. And we developed this approach 1 and extend it in the framework of Lorentz invariant canonical framework as a tool for realizing higher gauge symmetries. So first, of course, this is canonical formalism. We treat generalized coordinates and generalized momentum as independent variables. So I start from coordinate type variables. And these coordinate type variables are space-time vectors in 11 dimensions as functions of Lorentz invariant proper time parameter tau. And I also introduce, in addition to matrix here, some some variable, which we call auxiliary, but actually this is also a sort of dynamical variable as a generalized coordinate. And I propose to call this variable as M variables and play some crucial role. And what we have proposed in 1919 paper is in terms of this notation. Okay. Sorry. We propose this quantity in terms of matrix commutators as a generalization of Nambu bracket. And this satisfies total skew symmetry and also the crucial fundamental identity that was actually proposed by Taktajan. He is not there. But I actually told him about this. But anyway, so using this structure, I define a matrix version of Nambu.
I didn't. Could you go back one time?
Okay, sure.
What was that 0, comma?
0, comma means that once you construct this combination, this component is supposed to be vanished. Okay? Then this fundamental identity can be established. So in using this structure, I define this matrix version of Nambu transformations in this way, and also I actually slightly generalize from this form to this form by introducing these gauge parameters to multiple pairs. That's possible. That does not violate fundamental identity. And I defined generalized gauge transformation in this form. So this looks like ordinary SUN transformations. So this is additional part. But the merit of making this generalization is that these two components can be treated as completely independent. That is more convenient. And if you use this form, this is a bit cumbersome to do that. And also, one of the characteristics of this generalized higher gauge transformation is that any single matrix, if that is associated with non-zero m variables, can be gauged away to the unit matrix. Okay? That is a new feature of this generalized transformation. So, because of the presence of this term. Okay? Oh, again. Yeah. Then we can first construct some invariant under this transformation using in terms only of coordinate variables. So that plays a lot of potential term in my covariant action in this form. Okay. Oh, again, it's very difficult to use this. Okay. Yeah, in this way, okay? And I also introduced, I said this tau is invariant proper time, Lorentz invariant proper time. So in order to make this action or following construction as relativistic invariant, and in order to preserve reparameterization invariance, I introduced Einbein satisfying this relation. And here, this quantity here is defined in this way, just the product of matrix part and taking trace. So then I also introduced momentum time variables as a canonical conjugate to the previous generalized coordinators in this way, okay? The matrix part, and also some counterpart to the m variables in the coordinate space. And basic requirement is that canonical structure should be preserved under higher gauge transformations. And also, please keep in mind that this, if you use this, put P here, this is just ordinary Poisson bracket, okay? Not the matrix Poisson bracket. That is rather confusing, but please keep that in mind. Scalar. But of course, a vector in the sense of 11 dimensions. But in the sense of gauge transformation, that is scalar. Okay. So, and because of this requirement, we can determine the transformation property of momentum part uniquely this way. Okay. Of course, the transformation is rather different. If you only consider this ordinary part, this is the same, but always we have some additional transformation due to the existence of m variables. And this is, of course, this preserves canonical structure as by definition. And because of that, we can express this transformation using a generator this way. Oh, only 6 minutes left. Okay. So, and also, I have no time to explain this detail, but I further introduce symmetries. One is scale invariance with respect to the scaling of proper time, and also another gauge symmetry, another higher gauge symmetry, in order to eliminate negative models associated with the 11-dimensional Lorentz metric, okay? Space-time. Because I require that canonical formalism is to be invariant and Lorentz transformations. Instead of canonical delta, we have to use this yet Lorentz metric. So necessarily we have some kind of negative mode, and that should be eliminated by using some kind of higher gauge transformation. That is the role of this transformation. Sorry. Okay. So as a whole, gauge symmetries are actually generated by these generators. We have 4 components of gauge transformation in this way. So here is a schematic structure of higher gauge symmetries like this. Okay. So on the baseline, we have ordinary matrix that as 11-dimensional vectors. And if I put hat here, that means that the traceless part. And that is actually mixed to the trace part, or center mass part, and also auxiliary M variables in this way. That is a schematic structure of these higher transformations. So, because of my basic requirement of that these transformations keep canonical structure, we have necessarily have invariant, which contains derivatives as Poincare invariant in this way. Okay. And of course, I have introduced gauge transformations, so derivative should appear in the form of covariant derivatives in this way, and associate. To do that, of course, we have to introduce gauge fields. But I have no time to explain that in detail. So in essence, we have constructed a symplectic structure, not metric structure, which is invariant under generalized and discretized Nambu transformations. So now we are in a position to write down Lorentz invariant action in this form. Okay? Oh, sorry. Okay. So this first line is just for Poincare invariant into form which is separated into traces part, and also auxiliary part. And the second line consists of two terms, the ordinary kinetic part and potential part in this way. And also I have introduced some kind of further additional variables as a kind of Stuckelberg type variable to keep this higher gauge symmetry, which I introduced to eliminate negative mode associated with Lorentz metric. And this action are characterized by these four kinds of transformations. First, of course, by definition, that is local repermutation invariant with respect to tau. And also, this is characterized by global transformation invariance, and also additional transformation invariance in this auxiliary space. And because of that, we have two conservation laws in this way. Center mass momentum is conserved. Also, this coordinate M variable is also conserved. And also, there's a global scale symmetry. So there's no scale parameter at the beginning in this theory. And also, of course, most crucial, higher gauge symmetries, which consist of four parts in this way. Okay? So because of this, corresponding to local symmetries, we have constraints. First, corresponding to Einstein, we have mass-share condition, relativistic mass-share condition. So, sorry, I'm not used to this. Okay. So, mass-share condition, relativistic mass-share condition. So as I promised, this part is, of course, manifestly Lorentz invariant. And also, there are Gauss constraints of four types in this way. So this first line is just correspond to ordinary generator of SEN transformations. And these three additional Gauss constraints, which is associated with higher gauge symmetries. So in a sense, we have two conserved vectors like this. This P sub means that if I put this subscript circle, that means that the trace part or center mass part. And that is conserved. And also, as I said, this XM is also conserved. So we have, usually if we have some many body status, we always had some preferred frame, which is center mass coordinate. But in this case, because due to the existence of higher symmetries, this preferred frame is replaced by some kind of two-dimensional structure, which I call M plane, or more appropriately M plane, instead of center mass plane. So this makes us possible to this to be gauge equivalent with light-cone matrix theory. So I have no time to explain detail. So if you make light front gauge fixing, then due to the existence of these four kinds of new Gauss constraints, actually this Lorentz invariant structure actually reduced to light cone by eliminating completely the traces part of light components of these variables. So in this way, we arrive at this desired result with this relativistic invariant mass square actually reduced to this familiar form with this constraint. And also, if you look at the center mass part, then we have this. Okay, let me have a few minutes. So here, also another interesting thing appeared, because if you have consider some large SEM large systems with n times n matrices, we can always decompose into subsystems, and subsystems should also be treated in the same way. And I have only introduced one Lorentz invariant prototype. So every system must be synchronized in that single time, and that is only possible when this is independent of n. And because of that, we necessary to have to force this constraint. This is essentially light-cone compactation condition. So in that sense, DLCQ compactation condition is an automatic consequence of the synchronization with a single invariant proper time. So I'll skip this. Because you can also consider BFFS1. Then we have a very complicated volume effect-like effective action. But if you take large n limit, then you arrive at the same system. And this is consistent with the original BFFS conjecture. Okay. So, and of course, n variables also play other roles. First, the system is scale invariant. But if we assume that as an initial condition of the universe, we have some non-vanishing xm, then of course that causes a spontaneous breaking, a kind of spontaneous breaking of global scale symmetry, and that produces the fundamental scale of M theory. And the original theory is completely scale invariant. That means that we have only one fundamental scale in each sector, and that sector should be treated independently as a sort of superselection rule. And also, this variables plays the important crucial role to establish supersymmetry by providing a natural covariant projection conditions on spinors in this way. And I arrive at total action, completely manifestly Lorentz covariant, and also satisfy a global supersymmetry and also dynamical supersymmetry. So, conclusion. I hope that this is not a garbage for Spencer. So hopefully the present covariant formulation of metric theory will be useful as an intermediate step toward the construction of M theory. But of course, there are many issues remains to be clarified. I only discussed this construction of covariant action. I haven't discussed any use of this framework to discuss the dynamics of various blends, in particular in the large n limit. I also assume this flat background. Of course, we have to understand what is the deformation of background and related problems. So problem of background dependence or independence. And also another interesting question is whether it is possible to covariantize matrix string theory in this way. That does not look so simple, but maybe a possibility. And also another difficult question is how to include anti-degenerants. That is very difficult. And of course, there's many others, perhaps. And my guess is that ultimately we should develop some kind of field theory of matrices. By field theory of matrices, I mean that basis space of field should be a matrix. Or maybe we can call that the field theory of deviance. Okay? But that is also a very difficult question. Also, I have tried for some time to do that, but not yet successful. So finally, I would like to, so as a final speaker, I have to do this perhaps. So I want to thank the organizer of this very wonderful, impressive meeting. It's Avinash and Rejesh and Shiraz. Thank you very much. Also, okay, thank you. And of course, finally, congratulations again for your 65th birthday, Spencer. In Japan, we say, as a common sense, that 60th birthday is the time of rebirth. But I think nothing prevents us to say the same to 5th birthday here. I'm not sure whether this is appropriate or not. So I hope Spencer is born again, just now, maybe. And we have another and still more fruitful life. Thank you very much.
Any questions? Okay, let's thank Tamiaki again.